right, we're going to go ahead and get started, everyone. So thank you, everyone that's here in person and everyone that's on the live broadcast. Welcome to the 4th Annual 2022 UK Conference that's hosted by the HBC Advisory Council and DRAC. So I'm very happy to see that we're actually doing this in person again. So it's great to see everyone. We're hoping to do more of these again as time continues on in a very positive manner. And of course now we're doing everything hybrid. So we're live broadcasting. So for all the speakers that we have, and we have about 20 sessions over these next 2 days, we will be having questions come from not only the audience here, but from the questions coming from the stream. So I'll be giving you those questions as they come in. But I'd like to welcome you all. I'd like to thank our media sponsors, HPC Wire, Inside HPC, Scientific Computing, Intersect 360, and the Next Platform for their ongoing support. And we have a great 2 days agenda, like I said, and I'd like to have it all start off here with Gilad Shainer, who's the chairman of the HPC Advisory Council. And Mark, if you wanted to say a couple words too, it'd be great. So please,
Mark.
Let's have Mark start.
It's his place.
And we get to have fun with the mic. So we are recording all the sessions, all the presentations, and the videos of each session will be available later on the conference website.
Thanks,
Thank
Brian.
you, Mark.
Thank you. So good morning, everyone. I'm Mark Wilkinson, Director of the DRAC HPC facility, and I'm Professor of Astrophysics here at Leicester. It's great to see you all here. We didn't know when we were discussing whether to do this conference in person or online earlier in the year. We weren't sure how many people would come, but in fact we have about the same number of people in person this time as we did before the pandemic, so that's great. So thank you all to everyone who's here in the room, and hello to everybody who's online. So, as Brian said, a very interesting agenda, so I'm not going to say very much. Just want to welcome you all to Leicester. I hope you like the facilities, and if you're staying here, that the accommodation is good. Just one housekeeping thing: we're not aware of any fire alarms, fire drills rather, planned for today. So if the fire alarm goes off, follow the signs to the exits, which I meant to check where they are, but I'm sure they're through the 2 doors behind you there. So if the fire is over there, go out that door and follow the green signs. The other thing we wanted to say, the final session of the day is TBD, and we're opening that up. We're going to try this as what I think is called an unconference session. So at coffee time, there'll be a list on the registration desk. If there is a topic you would like to suggest for a panel discussion, if there's a talk you would like to give or a talk you would like to hear, you can put that down. Just note, if you nominate somebody else to give a talk and you don't ask them first and they decline, then you have to give a talk. So just be careful. But yeah, we'd like to hear what you would like to cover in that session. So it's a 45-minute slot. It can be a panel discussion about a topic that you're interested in, or anything else you would like to suggest. So please sign up for that during the coffee break. And with that, enjoy the next couple of days. I'm really looking forward to it, and hope we have a great workshop. So now I'll hand over to Gilad.
Thanks, Mark. So we did prepare some slides. Actually, Brian prepared some slides. It's actually good to be back, physical event. No, I've never seen Brian with a suit and a tie. Couple of times. I think even when you got married, you didn't wear it.
Shorts and t-shirts.
Shorts and t-shirt. Exactly. So I think that's the first physical event after COVID that we're actually doing. I think the next one we also plan to do a physical event finally. So going to the hybrid model of physical meetup, physical events, physical conference with a streaming part. So first time, last time was 2019, so we had a small gap. Hopefully not continue with that. Let's see. There we go. Yes, no? How do you flip the slides here? Oh, here we go. Now it works. So we have 2 days, I think, multiple different kind of topics. So it's essentially from a council perspective, we're trying to touch multiple topics and not just focus on one area in the world of high performance computing, but looking on technologies and usage and applications and so forth. So 2 days, different kind of topics. If you do have any feedback for us for future conferences or future events about topics that we didn't cover here, and those may be interesting topics that we should look to cover in the future. There is an opportunity today, for example, if you see something is missing, there is the last session, open session today, that we can use it as well. A little bit about the council, so give you an update of what we are working on, what we're doing. So the council was established in 2008, long time ago, almost a century ago, with the mission to bridge the gap between HPC usage and the potential, trying to bring more knowledge of HPC first to young people, universities and students, and I'll talk a little bit about what we're doing there, as well as to create collaborations and explore different kind of things and trying to look into the future and stuff that can be done. We have more than 430 members. Some of them are utilizing the resources of the council. Some of those are contributing resources to the council, and so forth. Membership is free, so if there is entities that are not members of the council, they're more than encouraged to join us. So several things that we're doing. First, we're operating a small compute cluster. We're not focusing on size and scale, but we're focusing on variety. So different kind of compute elements, different kind of networking storage, software setting, and so forth. And it gives us the ability to explore different kind of technologies and the impact of those technologies on applications. How to optimize, how to build stuff by yourself. We build recipe for storage connectivities and how to utilize data processing units, which is a new entity in HPC and so forth. We're using the center for a lot of best practices and research that we're doing. And this center is also open for members, free of charge. If other people want to do their own testing, their own explorations, qualification of different kind of software elements, there is a free access to those resources. We continue with something that we find very important, which is releasing application best practices. So what we're doing is we're taking different kind of workloads, different kind of data sets, and we're exploring different kind of things. It could be the impact of new technology generations. It could be impact of different kind of software elements, could be different kind of MPIs, different kind of compilers, how many threads you want to use, what's the optimized number of threads versus cores, and so forth. And we publish all of those results. A couple of the things that we're focusing recently, one is we're trying to better quantify the impact of latency on different kind of workloads. We all know, latency is very critical for scientific computing, and on the other side, bandwidth is very important to AI applications in that sense. But there are things that, first, there is element, or these elements is something that you want to quantify. The second is you want to see the relationship between those things. So we start looking on doing quantification of impact of latency on different kind of workloads, different kind of data sets. And there is some interesting results around that, and we're going to publish that shortly. But definitely there is a very dramatic impact of latency on different kind of scientific workloads. Actually seeing that adding around 500 nanosecond on a data latency can impact different kind of workloads by 30%. So it's kind of actually a big impact, but I think the first time we can quantify that in that detail. The other part is utilizing of data processing units, which is new entity or new compute entity in supercomputing environments. And one of the things that we believe in is that we will see a dramatic increase of entities and application that needs high-performance computing, that needs access to supercomputing. So we'll see an increase of amount of users, an increased number of applications, and obviously the combinations of AI and scientific computing will also drive that. And that means that on one side, cloud infrastructures will want to probably provide more and more HPC services. So they will need to change their infrastructure, the way that they build their infrastructure, because it's typically not built for that. On the other side, supercomputers entities have a great opportunity to be able to serve those growing amount of users, but they need to change the way that they operate. Because right now, supercomputer, it's an open environment. It's not built for a multi-tenant environment. And most of the HPC clouds out there are not really built for HPC. They're built for small-scale testing. One of the potential hardware element or platform element that can enable that, meaning bringing multi-tenancy to supercomputing or helping to move HPC clouds into actually a supercomputing kind of a class, is the DPUs. So that's why we think this is an important element that will change the way that we build things, and there is a lot of research that we're doing around that. Last week we did the first hackathon in the UK around DPUs. There were a few teams. We hope there's going to be more teams, but it's the first time. So we had a couple of teams from the UK. There was a team from Barcelona, for example, they joined, and others. So we will see that growing, and this is another thing that we are focusing on. Student cluster competitions or workshops, this is something that is very important to us. It's kind of creating the next generation of scientists and next generations of professionals in world of HPC. So we're managing several competitions. We're managing the competition at ISC in Germany. That's an annual one, and then we're also managing a competition, regional competition in APAC. And then we help in the competition in South Africa, and we're helping some other regional competitions around the world. Those competitions typically include training and as well running on systems. So there's competitions that the students need to build their own system. They need to build their own supercomputer. We used to have a power cap on it for 3,000 watts. Next year we're going to change it because 3,000 watts, I can bring one device and it's 3,000 watts. So we're moving that to 6,000 watts actually. So will enable to go back and build at least a couple of nodes when you're building a physical event, or building a physical system and not just a single box. So we're doing that. The second part is we try to give them tasks that requires dealing with a new generation of elements, and also tasks that requires them to go and log into some supercomputers. And we have collaborations with Toronto and Pittsburgh, Singapore, and we're doing 2 more. So actually having great collaboration with those entities, and those entities give access to the student to their supercomputers. So they actually go and work or use supercomputers and get experience on that. We're also doing programming workshops, by the way, and participating in summer schools in Stanford, and bringing new topics for students to learn and discuss with us. And then conferences or technology meetups, in a sense. So we're doing several. We moved to use everything. We moved to do everything virtual in the last 2 years, 2-something years. Now we're back to physical. So happy to open the first physical event here in the UK. We looked forward to come here, especially for the food. It's one of the things that draws us to the UK. And coming to last year, of course. Next one, I believe the next one's going to be in Switzerland, if I remember correctly.
Might be Stanford first.
Maybe Stanford first, right? Either Stanford or Switzerland. So those will be back physical events, and then we plan the rest of next year to be physical events, unless something else is going to happen. How to reach us? You can go to the website or contact us through the email. The things that are relevant again, so if you want to join and there is entities that are not members and they want to join, it's free of charge. You get access to the system centers that we have, and then you get closer access to the things that we develop, or the research and the publications that we put out. If you want to help with the student cluster competitions around the world, more than happy. We have folks that helping on training, on different kind of workloads, for example, judging. It's also important, so they can actually talk with the students and help us to give them a score, or to help to give them the right feedback. As well, if you know about a system that we should talk with the owners, try to get access to more systems so the student can actually leverage more or different kind of architectures for their competition. That's going to be great things. So with that, I want to thank Mark for all the collaborations, else we wouldn't be here in Leicester. Maybe I need to blame you. No, I'm kidding. To Dan Olds, that following us and helps to record everything and also to present from his own research. Brian, which dressed greatly, suit and a tie. This is a picture to remember. So, for all his support, obviously. Gabby, which is on the other virtual side in the US, that helps with all the operations and so forth. And for DK, especially for DK Panda, is joining us for all the physical conference that we're going to. And you go typically on Delta, right? So they liked you too. From that side. And everyone here, thanks for joining us, and hopefully that you're going to enjoy the next 2 days. Thank you very much, guys.
All right, thank you, Gilad. Let's see, start the video. Okay, so our next presentation comes from Dalia Chakrabarty from Brunel.
That should work. Okay. Thank you.
Thank you.
So hello, everybody. Thanks very much, Mark, for this invitation. This sounds like it's going to be an extremely interesting conference. I'm looking forward to this day, which is the only day that I can afford to spend with you. So I'm basically here to talk to you about some learning aspects related to systems that change with time. And in particular, I will be focusing on discussions about some kind of an AI infrastructure that we might want to build that would help to monitor these temporal changes that such systems are undergoing. So in the first part of the talk, I will basically focus on discussions about how the system is going to pan out in the future. What will be the state of the system at some time point in the future? And then I'll back that up with some discussion on the quantification of the size of the effect of some kind of an agency that is causing these changes in the system. So let me be a little bit more specific as to what this talk is going to be about. So as I said in the first part, we are talking about what is going to be the state that the system will be in at some time point in the future. And for this talk, we are going to basically address this issue of future forecasting by learning what I call the evolution driving function. So this is basically a function that tells me all about how the system evolves. So we're going to try and learn this function. We're going to forecast this function at some time point in the future, and then link the forecast value of that function at that time with the state that the system will attain at that point. Okay, so I'm going to show you, I'm basically discuss this methodology using an illustration on the forecasting of infection numbers of the pandemic. So thereafter, I'll move on to the second part of the talk, and there we are talking about this quantification or scoring of the size of the effect of this change-inducing agency, if you may. So the illustration of this will basically be in the context of oncology. So we're going to talk about the progression of a disease that's, well, often, unfortunately, not sometimes, but often afflicts patients who have received bone marrow transplants. So these patients, because of the transplantation, they have basically developed this disease, and we want to know how progressed is this disease in a given patient. So that's something that I'll speak to about in the latter part of the talk, but let's start with the first part. So as I told you, we are trying to forecast the future state of the system, but by learning the so-called evolution driving function, whatever that may be. That's something that, as I told you, it's basically informing on how the system evolves. So if I need to learn this function, I need to have the corresponding training data, right? So that training data in this context would then imply pairs of values of the input to this function and the value of the output of this function at a given input. So that input is basically whatever are the inputs to the evolution driving function, and then I would need the value of this function computed at a design input. But then I don't know the value of the evolution driving function at a given input. I have no idea what this function is at this point in time. So how do I even assume that there is possibility for me to learn this function? Well, let me clarify the problem that we have. So here, let's say that we are trying to basically learn the relationship between two variables, x and y, very generically. That learning of this relationship is equivalent to fitting a curve to this data, right? So that data points have been shown in these open circles. So these circles, these are the points that live in my training data set. And for each of these points, I know the x coordinate, I know the y coordinate. And if I know the x and y coordinate of all these points, then I know what to fit this curve to. But now imagine a situation where I cannot learn, I can't estimate, I can't guess. I basically have no observation, so I have no idea as to what the value of y is at a given value of x, called xi. So what am I going to do then? Well, then I don't know what I am to fit this curve to. And then I basically equivalently do not know the relationship between x and y. So I'm in a bit of a problem, and the addressing of such problems is what, in an upcoming work, I have tried to bring under the umbrage of what I call bespoke learning. So the learning of that y at a given x becomes bespoke to the problem at hand, to the data at hand. And I mean, at this point in time, and I could be wrong, there could be other methods for bespoke learning of that originally absent training data. But I think there are basically three ways that we can undertake the learning of a y under such circumstances. And really, problems like these abound across disciplines. And after the presentation, I could speak to about examples of such problems. So I was talking about the three types of bespoke learning that I think I've been able to identify so far. And the first is the exploitation of the dynamics of the system. So maybe we can exploit the dynamics of a dynamical system, and we will see how this leads to a value of y. So this really will be in action in the first part of the talk. Then for static systems, we can design likelihood functions in such a way that we can generate that originally absent training data. But then there is a third method still, which is kind of relevant when the x is a vector. So then I've got lots of components of this x, and I use the data that I have on these components to build a graphical model or a network of that data. And then I do that for another system as well, and I find the distance between the graphical model of this data and the graphical model of that data, and that intergraph distance tells me what y will be in this system compared to another. So this is a relative scoring of the y, if you may. So we will see that in action in the last part of the talk. So let's just go back to the first part of the talk where we are talking about the evolution driving function. So we will undertake the bespoke learning of this function's values at given inputs, and that will generate the training data. That will be all part of step 1. Then in step 2, I will make that learning of that evolution driving function possible. And I will also predict the value of this function, this time at a future time point. So I'm forecasting the functional value. And then in the third step, I will basically link that prediction with the state that the system will be in at that future time point. And the illustration is on forecasting of coronavirus infection numbers. So this is a very generic real-world system that I have. For example, this coronavirus application demands such a system. So here, I have to interpret my location and rate variables, my phase-space variables, in a very generic way. So for example, in this coronavirus application, my x, the location variable, is basically the number of infections of coronavirus. So that is what I've denoted with x, and in general, that x is a function of time. So the rate variable v will then be the time rate of change of this x. So that would, in this coronavirus application, basically be the time rate of change of the number of infections of the pandemic at the time point t. And the phase-space probability density function, or PDF, of the phase-space variables, that also becomes very relevant to our discussion. So that is denoted F, and I just want to introduce that notation to you because there's no escaping notation in this talk, unfortunately. So the claim here is that if I know the system to be deterministic, and I know what the state is that the system is in at time point ti, then I should be deterministically be able to predict the state at another time point tj, as long as I know how the system is evolving. Okay? So as long as I know this evolution driving function, and I can perform this state prediction at tj within Newton's second law. So all of you who have by now kind of recalled your Dynamics 101, you would have known that I'm talking about the potential function when I speak of the evolution driving function, right? So it's really the potential of this very generic dynamical system that I'm trying to learn. And that would require an interpretation of this potential, which will also have to be quite generic, just as it was for our rate and location variables. So the potential is, in my interpretation, it's a parameterization of how much effort I will need to input into the system to bring it from a state of minimal disturbance to the current state that it is in. Okay? And that too, in our work, we are going to linearly transform this potential so that its values live in the interval of -1 to 0. So I'm basically going to shift it by the potential of the state when the system is maximally disturbed, and scale it, or normalize it rather, by the potential of the minimally disturbed state. The important point to take away from here is, however, that potential is modeled as rate independent. So it will depend on the location variable, and in general it will depend on time as well. I mean, the form of the potential function can change with time, but in my model it doesn't change with rate variable. So what I've done is that I take the full range of time that is of interest to me, and I break it up into two parts. One is what I call the learning period, and then I have the prediction period. So the learning period is when I learn the potential, and then I predict its value or forecast its value at a future time point, and all these future time points will live in the prediction period. Okay? And that too, I partition this temporal range further. So I will partition it into time windows, and these time windows have a width of tau, let's say. At this point in time, we have used uniform binning of the temporal range. It's always possible to change that. Always, I say, but it's computationally demanding to undertake that. So for the time being, tau is fixed. It's something that I have chosen. And I've chosen it such that the system remains an autonomous and Hamiltonian dynamical system within each of my time windows. So what that means is that within any of my time windows, the system functions do not have an explicit dependence on time. So the potential function when the system is in the ith time window is basically it's basically dependent only on the location variable and not explicitly on time. And that location variable is, of course, changing with time, but the potential has a form when the system is within this ith time window that does not change until we have moved to another time window. When the potential form, the form of the function, that has changed when I've moved to another time window. But within a time window, the input of the potential function is definitely changing. It's varying with time, but the form of the function remains the same. And the same thing for the phase space probability density function. So this PDF remains a function of the phase space variables, location x and rate v, but no explicit dependence on time in the ith time window. But once you move to another time window, its shape may change. So in addition to this, the system is Hamiltonian when it is within the ith time window. That means that I should be able to suggest that the total time derivative of the phase space PDF in the ith time window is basically 0. And this is true for all time windows. So that would then suggest that I am able to recast the phase space PDF as a function of what I call integrals of motion. So very loosely speaking, these integrals of motion are basically functions of rate and location such that these functions themselves do not vary with time. So one example of an integral of motion is energy. So what we are saying is that the phase space PDF has now become a function of energy. And this is true in every one of my time windows that are living within that learning period. So now that I have expressed the phase space PDF as a function of energy, energy being the sum of potential and kinetic energies. Kinetic energy here is again very generally described, so it is half the squared rate variable. So now that I have got potential in the support of the PDF, that's actually a very useful trick. Because after all, it is this PDF is the density of the observables x and rate. So it's in terms of this PDF that I will define my likelihood, which is after all the probability of data given the model parameters. So the likelihood now has information about the potential, which is what we wanted to make an inference on in the first place, right? So this is useful, except there is a snag in what I just told you. The observables are not x and the rate. In most of these systems, the observables are just x, that is the location variable. And there is no observational information on the rate variable, which means that the phase space PDF is not the observable, the density of the observables. Rather, what I have to do is I have to integrate rate out of this phase space variable PDF, and only then will I get the marginal density of the location variable, which would indeed be the density of the observable. So if I am to look for the probability of the data, probability of all the observations given the model parameter, that is our likelihood, then I have to go for the density of the observables, which is what you get if you integrate rate out of the phase space PDF. And that integration of the rate can be done because I can identify values of the rate variable that are relevant to the ith time window. Okay, so I have carried out that integral, and what I now have is the marginal probability density of the observable location in that time window. So you compute this, this marginal density at each value of the observed location, assume your observations to be independent of each other, and that product will then give you your likelihood. So it looks like we've got likelihood in the bag. That's basically what is expressed in the first equation in this slide. Except we have to be aware of one thing at this point, and that is that these two unknown functions, namely the phase space PDF and the potential function, these cannot be learned at this stage, because I do not have the training data to learn either function. So instead what we can do is we can vectorize these functions. So what I mean by that is that you take the relevant range of the domain variables of either function and chop that range up into x partitions or energy partitions, and then hold the respective function a fixed value on top of any of these partitions. So that way the value of the function over the ith x partition becomes the ith component of what I call my potential vector. The notation is bold phi. And similarly, we can define a phase space PDF vector. So we've really vectorized these functions. So we can rewrite our likelihood in terms of these the vectorized potential and PDF functions. So now we have the likelihood in the bag. What we're going to do is we're going to invoke adequate priors on these unknowns, and the unknowns are now the components of the phase space PDF vector and the potential vector. So we will, if we have any strong priors on each of these unknowns, great. These will be inserted into Bayes' rule. That will give me my posterior probability density. It's the joint posterior of all the components of the potential vector and the PDF vector, given the data on the locations. Then I will generate posterior samples using MCMC. I use a metropolis within Gibbs algorithm to generate these samples, and this will then result in a marginal posterior probability density of each component of those two vectors, given the data on the locations, and I will use those marginals to compute the uncertainty on each parameter that I have learned, given the data, these uncertainties being the 95% highest probability density credible region in my case. So what I have actually achieved by doing this is really a potential vector in any of those time windows, right? So this is really what I was looking for in the first place. I was looking for a training data that will allow me to learn that evolution driving function, aka potential, and that's what I have now. At every time window, I have a potential vector that I have learned. So using this training data, I now start step 2 to learn the potential function. So this is now a vector valued function which takes time as its input. This is my potential function, which I'm going to suggest is basically a sample function of some stochastic process. Now, for generality of the model, for ease of computation, I'm going to suggest that this stochastic process is a Gaussian process. So my vector valued potential function is a sample function from a vector varied Gaussian process, and then by the definition of Gaussian process, it implies that the joint probability of a finite number of realizations of this potential function is then the high dimensional equivalent of the multivariate normal density, which is a matrix normal density in my case. So these are technicalities, but that's basically what you get out of this modeling strategy. So what are these realizations of the potential function? So these realizations are basically the values of the potential vector that were learned at each of my time windows. So if there are n time windows within my learning period, then I've got n number of such realizations, the joint probability of which is my matrix normal density. So don't worry about the mean of this matrix normal density. I can standardize my potential vector data, and that will suggest that it's okay to use a so-called zero mean GP. So the mean of this matrix normal is basically known. It's a null matrix. But the two covariance matrices, that's something that we have to learn. There are two covariance matrices in a matrix normal density. So let me just schematically talk to you about what these are. What information do they carry? So what I've done here is schematically list for you the components of the potential vector that I've learned in the first time window. Let's say I've also done it in the second time window, the third time window, and so on till the last time window within my learning period. And thereafter starts the prediction period, which I'm not thinking about now. So you can ignore that bit. So think about the possibility of finding the covariance between the potential vector that has been generated at the ith time window and that which is generated at the jth time window. So that those vectors are basically encircled in these red ellipses that you can see. So that covariance will become the ijth element of the covariance matrix that I call sigma subscript time. Okay, and you can also form vectors which would be the ith component of the potential vector, its values that have been learned across the different time windows. And then you have the same kind of a situation with the jth component of the potential. So those are encircled in the green ellipses. So the covariance between these green ellipses will then give me the ijth element of the other covariance matrix, which I call my intercomponent covariance matrix. So there are technical ways for us to learn and estimate these two covariance matrices now that I know what they are. And the important thing is that once we know what these are, and I can talk to you about the technicalities after the talk if you're so interested. The point is that if we do know these two covariance matrices, I can perform closed form prediction of the mean and the variance of the potential vector at any other time point. And for us, that other time point, it lies in the future. Okay? So that way we have basically forecast the potential vector at some time point into the future, which is that time point being chosen by us. But now we are in step 3. We try to link that forecast potential vector at some time point in the future with the state, namely the values of x and v that the system will attain at that time point. How do we do that? Well, we first invoke Newton's second law, and then we define what we call our x vector and our rate vector v, where if you recall the vectorization of the potential function, I suggested that you take the domain variable of the potential function, namely the location, take its relevant range and chop it up into x partitions. So the centroid of each of those x partitions is a component of this x vector. Okay. And then similarly, the rate variable is defined just as the time rate of change of that x vector. So when we include these definitions, we include some independence information, etc. in Newton's second law, we come up with a very useful result, which is that the Euclidean norm of that rate vector is basically what I can identify in terms of the potential vector that I have forecast at this future time point. So that is given as square root of 2 times what I call the negative forecast potential. So the negative forecast potential is really a linear combination of the components of the potential vector that was forecast at that future time point. So having known that, I now know what my forecast rate is. And the forecast location at that time point in the future is basically obtained by integrating over the rate from time equal to 0 to this time point under consideration. Okay. So I have basically used this modus operandi to learn the values of a variable, a location variable called x of t that I have defined as half the log of the number of coronavirus infections in 8 different countries added in quadrature. Okay, so the values of the infections in these 8 countries, that was taken from the WHO dashboard, and our learning period extended from at the end of February in 2020 till about the middle of September in 2020, and that accommodated 13 time windows, each of which tau, which was 15 days in this application. And thereafter the prediction period started, so the prediction period went from the middle of September of 2020 till about sometime in June of 2021. And the prediction period included 19 time windows. So I will show you the results of learning from the first 13 time windows within the learning period and the results of forecasting in those 19 time windows within the prediction period. So just one other thing to let you know, that the components, there were 20 number of components of the potential vector by choice, which was a data-driven choice. Okay, so how do I know that my forecast is good? Well, I can always compare the forecast quantities with the empirical quantities. So I can compare the forecast rate with the empirical rate, except I told you that rate is not empirical. It's not observed. Only location is observed. That is true indeed. So empirical rate will have to be an approximation that will be given as the difference between the observed locations separated by one time window, which in my case is a day. So that's how I'll have the empirical rate, which I will compare with the forecast rate. And I can, of course, compare the empirical location to the forecast location. At the same time, I can compare something in terms of the potential. So I basically recall that there is some kind of a transformation of the forecast rate that gave me that negative forecast potential, if you recall. So I can slap that same transformation on the empirical rate, and then I can get my negative empirical potential. And I can compare the negative empirical with the negative forecast potential. Not that that's going to give me any added information compared to what I get by comparing the rates, but that's another plot, basically. Okay, so here are the results from the learning period. So if you recall, my x was defined as half of log of the coronavirus infection numbers added in quadrature. So I exponentiate my x, and I plot these number of infections now with respect to time in days. That's shown in the bottom right. And these are plotted along for each of those 13 time windows in different colors. And in the corresponding colors, on the top panel, you can see the potential components that have been learned. These have been plotted against x perf x. And now if you normalize your x perf x, all these potential profiles, they sort of fall on top of each other, and that's shown in the top left. Now, one thing that I did not speak to you about was the probability density function vector, or the PDF vector. We did learn the components of the PDF vector at each each of those learning periods, time windows. So when we plot the components of the learned PDF vector, the plot that you get is basically in the bottom left, and they are in corresponding colors as well. So the important point to take away from that plot is that though functional learning of the PDF hasn't been undertaken yet, but we can see that the data suggests that there is no reason to believe that there will be, that PDF, the function itself will be locally monotonic. There are deviations from local monotonicity as suggested by these plots in many of the time windows, and there are definite deviations from normality that you can get by looking at these plots. But of course the last word on that hasn't been said because I haven't learned the probability density function yet. I only have the training data to make such learning. So here are the results from my forecasting. So if you just concentrate on the top two plots, those are what, top two panels I mean, those are really giving us the forecast quantity in black superimposed with the error bars, and the red are the quantities that are empirically observed. So I would suggest for the time being that you ignore the profiles in green in the top panels for now. And then in the bottom left, you basically have X that has been plotted against time in days, and the red curve that you see there, that is basically the 15-day average. Now that 15-day average has been replicated in the bottom right panel as well, with the daily value of X plotted in green, and our forecast for the location is bound by the outermost of the three thin lines that you can see that superimposed on that plot. So I just want to make some comments on the quality of our forecast. The first thing that I would say is that in the top two panels, which respectively show the rate forecast compared to the empirical rate and the negative forecast potential compared to the negative empirical potential on the right. So if you go back to the rate picture on the left, then you can see that the quality of prediction is not bad. I mean, there are time windows within this prediction period that where we actually miss the correct or the empirical value of the potential, which we know in hindsight. Empirical value of rate, I should have said, because we're looking at the plot on the left, which talks about rate. So that happens, for example, at that 25th time window, as you can see, and it also happens in the 21st time window. Now, this result is actually something that fills me with confidence about our work, because at these time windows, what is happening is that the information that is coming from the past in the time series is actually suggesting that the forecast rate should go up, not go down. And in spite of that misinformation, our method has the power to defy such wrong information. And basically the rate has gone down from the 24th to the 25th time window, as you can see, but it hasn't gone down sufficiently enough to match the empirical value. So there are shortcomings in the method, but it is at least defying information redundancy when information redundancy is basically wrong at the current time window, which also means that any kind of a parametric time series model that bases its forecasts on nothing other than what is in the past in the time series is going to do badly. So that is where these green lines they come in. The green data basically are outputs from the so-called best fit ARIMA model. So that's a parametric time series model, and the model that was considered best by looking at the data that was the forecast data during the learning period, as well as the first 7 of the time windows within the prediction period. That is the output that is shown in green in the left. And another best fit model for the potential data over the same temporal coverage is shown on the right. So I don't have to say anything. The plot speaks for itself when it comes to the comparison of these parametric time series models and our work. The other thing about the potential so-called best fit model is that the scale of that potential model is not what is shown here. The output that you get from ARIMA is it takes the potential entirely out of the axis range that I've used in this plot. I tweaked it so that you could see the output within the same axis range. In other words, the potential even the best fit model, where the potential forecast is pretty abysmal. But now if you change the temporal coverage over which this ARIMA model is trained, then you get the results which are in magenta. And that's even worse. And the same problem holds for the potential forecast. So this is basically just to bring home the point that parametric time series approaches that base their forecasts on information redundancy alone in the past part of the time series, those don't work. Hidden Markov models might be a good idea, except that hidden Markov models slam a parametric form, and often a normal or a skewed normal or truncated normal form, on the underlying probability density function. And that does not work in these real systems. So the empirical dynamical models, that seems like a good idea because we are getting dynamical information into forecasting, and that's good, except they seem to be honing on only one marker of dynamics, namely attractors. And of course, nonlinear dynamical signatures are more than what is included only in attractors. So I think this is work in progress, but there is, hope in these kind of approaches. So as far as computational issues are concerned, the first point is what I would like to bring to the audience that we have here, to yourselves, because you can correct me on how hard or easy it is to basically perform Bayesian inference in a parallelized setting. We had tried this some years back, but could not go ahead. So basically, the advantage of this method is that the forecasting from one time window to another, that takes about 2 minutes on my Linux running laptop. So this looks like something that we can reduce with our further work that we are undertaking currently with one of my PhD students in Brunel, that's Kane. But I think I now need to move on to the second part of the talk. I've spoken enough about future prediction. So here we are talking about, if you recall, the quantification or scoring of the effect of an agency that is causing change, temporal changes to a system. So as the system changes, there are system parameters which are basically evolving with time. So we managed to accrue time series data on these system parameters. Okay, so that's something that we'll keep in mind. But what we are really after is a quantification or a prediction of the score of the effect of this change-inducing agency at a pre-change stage in a system. So the system has got some pre-change parameters that tell us about how susceptible the system is to such change. So knowing those parameters, which I referred to with the notation capital Y, knowing those parameters, how can I basically predict a score for the effect of this change-inducing agency to have changed this system? So that's basically what I'm trying to ask. Now, to make a prediction of that score, I would need to know the relationship between the Y pre-change variable and S, the score variable. Except that that would demand a training data set that contains pairs of values of S and Y. And I do not know the scores, so I do not have that training data at hand. So it looks like I can't learn the function between S and Y, and I can't, unfortunately, then forecast S, or rather predict S, for a given pre-change variable set Y in a given system. So this brings us back to the realm of bespoke learning. So it seems like if I can somehow manage to know the score of this change-inducing agency, then I'll be able to generate all of the desired results. So that's what we do using random graphs, as I'll just talk to you about now. So if you recall, we talked about these system parameters that were evolving with time as the system is changing. These system parameters are what I call theta 1, theta 2, and so on till theta m. So on all m number of these system parameters, I've got some time series data for a given system. So I'm going to construct a graphical model or a network of this data, of this time series data. And then I'm going to basically see how that random, or how this graphical model rather, compares to the graphical model for another system. But really, just to let you know that this graphical model is built of realizations of a random graph variable. So here my variable is a graph variable. And that means that as I'm undertaking an MCMC chain to learn that graphical model, I have a posterior probability density of that random graph variable given the data on theta 1 to theta m in the ith system. it's actually given the intercorrelation between theta k and theta L that I need to know for all pairs of k and L in the system I. So it's the intercorrelation of data in system I that is what the posterior of the graph variable is conditional upon. So I know what that posterior is, and I know the posterior probability density for the graph variable given data in another system. And I can compute the distance between these posterior probability densities. One such distance is the Hellinger distance, which is what I have used. So in our model, we suggest that this intergraph distance is basically proportional to the absolute of the difference between the scores in these two systems. And that too, in our work, what we say is that we've got this set of systems, and out of these, I'm going to choose one of the systems as my so-called reference system, and that choice is entirely arbitrary. I'm simply going to say that this system has got a score of 1, and then I try to find the score of every other system relative to the score of this reference system. Okay, so it looks like I have been able to find the reference score of each system in that set. Now, I also have these y or the pre-change variables, so that these could be paired up with the score that I have just learned, and that will give me the training data that I was looking for. Well, so this has been used to basically compute the progression of a disease that is called the veno-occlusive disease, or VOD, and this is a disease that often sets in patients who have undergone bone marrow transplantation. So these are patients of different kinds of blood cancers. They undergo this bone marrow transplant in the hope that it'll be a cure, and as a complication of the transplant, they sometimes develop, quite often actually, they develop VOD. Now, a VOD, the terminal nature of VOD is quite severe. The mortality rates can be as high as about 80%. So basically, what the oncologists wanted from us was some kind of a score for VOD onset and progression in a new patient who will be coming to them at the pre-transplant stage. Okay, so this is where our interest in this project came to. So any kind of a score that is given by oncologists that says that this patient has a severe VOD or a mildly severe VOD, in other words, any kind of a categorized score is firstly not enough. We need a continuous valued score, and that too, there is ambiguity between the symptoms of a VOD and some other complications that the patient at this situation might manifest. And that means that this kind of a expert elicited sort of a severity gradation might not be reliable. So we wanted to find an objective continuous valued score. And we had a retrospective cohort of 25 patients. So these patients have already undergone the bone marrow transplant, and we basically had the time series data on their physiological parameters. So these parameters would be like body weight, temperature, blood pressure, etc. So we had time series for each of these patients, and we also have the pre-transplant parameters for these patients. And these pre-transplant parameters would be like comorbidities, like the type of cancer that they are suffering from, etc. So using the time series data on the physiological parameters, we computed the graphs. Using the intergraph distance, we basically formulated that originally absent training data, using which we then learned the relationship between the pre-transplant variables and the score variable. And basically then we learned the value of the score for a new patient or a prospective patient for whom the pre-transplant variables are known to us. So this really is the workflow for this work. So we've got the retrospective patients and their physiological data in the form of time series. Now it's important to note that not all of these time series have the same temporal coverage, and that is because some patients, they die prematurely. So we basically build their graphical models, and using the using the intergraph distance, which we call delta, we then compute the scores. Now, this computation of the scores cannot be done deterministically from the intergraph distance delta, as we call them, and that's because it is the absolute of the difference between the scores that is my intergraph distance in this model. And then to ensure that internal consistency is obeyed, we really need to learn the scores using this intergraph distance. distance within an MCMC paradigm. So basically the scores are learned for each patient with uncertainties, and then we use these scores to generate that originally absent training data, invoke their pre-transplant parameters, and we have learned the relationship between S and Y, using which we can now learn the VOD score of any patient who is coming in as a prospective patient given their pre-transplant parameters. So here are the results of some of the graphical models that we have learned. In the middle is the graphical model of the patient who was chosen arbitrarily as the reference patient in our cohort. So the score of that patient is 1. And on that scale, the patient whose graphical model is shown on the right has got a score of 1.55 approximately, and the graphical model on the left is of a patient who has been learned to have a score of about 0.44. So as I told you, we use the intergraph distance, the deltas, to make a learning of of the scores, and the marginals are on each of these score variables are then learned, and 6 of these marginal densities drawn as histograms are shown here for 6 of the patients in our retrospective cohort. Now, using these, we learn the 95% HPDs on the scores and the mean of the scores for each of our retrospective patients. And then what we did was we cross-referenced against the score that we predicted with the VOD status. Did the patient develop VOD or not? And we found that all the patients who basically had scores of more than 0.11 in our choice of the reference patient, they went on to develop VOD. And all those patients who had scores of 0.11 or less were the ones who did not develop VOD. So this was really something that gave confidence that our method is working. Now, we used all of this. We learned the relationship between pre-transplant variables Y and the score S, and then we learned the scores for 5 prospective patients who, unfortunately, we predicted will all go on to develop VOD. But this was given to the oncologists at the pre-transplant stage, and that was very helpful to them, as they have told us, because they could tweak their treatment regimen. They could be more careful with some of the parameters that they were monitoring in patient care, and that is what resulted in a reduced severity of VOD, as has been told to us by our hematologist-oncologist collaborators. So that's really the results that we have so far. And talking about the computational issues, again, the forecasting of the score of a prospective patient takes less than 2 minutes on my laptop. And the learning part of the work can be done, but there is more work, more information that I need to glean from yourselves in terms of how we can improve that learning part of the work. And as far as the conclusions are concerned, it's important to say that physicians' priors can be acknowledged in our work. So for example, there was one patient who had a comorbidity of thrombosis, and thrombosis was not a comorbidity that any of the retrospective patients had. So we could not make an inference using information that this is an added comorbidity in this prospective patient. But the priors from the oncologist told us what that would mean in terms of the score, of the VOD score, and we performed a better informed inference as a result of that. So this is, of course, a very generic method of scoring progression of a disease. That's an important point to take. And we are already working with collaborators to give the mobility score in post-stroke survivors, and that's a work going on with colleagues from the Clinical Technologies Unit in King's College. That's really all I had to say. Thank you.